Have you ever stopped and wondered how your computer just knows how to get from point A to point B through this, giant tangled web of information? It really does feel like magic sometimes, but it's not. It's a strategy. And today, we're going to pull back the curtain on one of the most powerful ways computers explore the unknown. Let's dive in. I mean, think about it. You've got these two totally different problems, right? On one hand, you're trying to find the perfect study group in a massive university. On the other, you're trying to map out a train route across an entire country. They seem unrelated, but they're not. They're both about navigating a complex network. So how on earth do you do that without getting hopelessly lost? All right, so let's start with a fun little puzzle. Picture a huge group of students. Somewhere in that crowd, we're looking for these perfect little 3-person study circles. And this is a very specific thing. It's a group where everyone is teaching someone and at the same time learning from someone else. The key here, you see, is that it's a closed loop. It's not just a one-way street. Student A helps B helps C, and this is the crucial part. C has to be able to turn around and help A in a totally different subject. It's this perfect, self-sustaining little ecosystem of learning. Okay, but here's the catch. When you've got hundreds, maybe thousands of students, how do you find these hidden gems? You could try the brute force way, right? Check every single possible combination of 3 students. But that would be, well, as the folks who studied this put it, just painful. It's a non-starter. There's got to be a smarter way to do this. And there is. That smarter way is called depth-first search. You might have heard it called DFS. It is such a beautifully simple, almost intuitive strategy for exploring any kind of network. It's less about having a perfect map of the whole territory up front and more about having a really solid plan for your journey. The whole idea behind depth-first search is basically this. Pick a path and just go. Go as deep as you possibly can, follow that one single trail until you either find what you're looking for or you hit a dead end. And only then, when you can't go any further, do you backtrack just a little bit and try the next path. So let's actually watch this thing in action. It's easier to see than to just talk about. We have to start somewhere, so we'll just randomly pick student 8 and let the search begin. All right, so from student 8, the algorithm sees a potential connection in maths to student 9, and it doesn't hesitate. It immediately dives down that path. Now we're at student 9. It looks for another path, finds one in physics, leading to student 13, and again, it goes deeper. We're still on that one single trail. Okay, now we're at student 13. The algorithm looks for a chemistry connection, and what do you know? It finds one, and it leads right back to student 9. But hang on a second. We've already been to student 9 on this exact trip. And that right there, that's the aha moment. That's the algorithm basically saying, oh, we got a cycle. The second you hit a place you've already visited on your current path, you know you found a loop. Now this one's a 2-person cycle, not the 3-person one we were hunting for, but the point is the strategy worked. It found a hidden circle. So let's just recap the game plan here. You pick a path and dive deep. You leave breadcrumbs marking every spot you visit so you don't get lost. The second you run into one of your own breadcrumbs, boom, you found a cycle. And if you hit a wall, no big deal. You just calmly backtrack one step and try the next door. It's simple, it's methodical, and it works. But here's where it gets really, really cool. For our student problem, there's no map of all these connections sitting around. The network, or the graph as it's called, doesn't even exist before we start. The algorithm literally builds the map as it explores. So think of a train map, right? That's a pre-built graph. You can see all the stations, all the lines, everything is known ahead of time. But our mentoring network, that's what's called an implicit graph. The connections are just possibilities hidden in the data. We only figure out a connection exists at the exact moment we need to decide where to go next. So how do we make that calculation, fast? If we have to check everyone every time, we're back to square one. Well, there's a really clever trick. If you pre-sort the students by their scores in each subject, finding the next possible connection becomes instantaneous. It's a simple hack that makes building the map on the fly incredibly efficient. Okay, so now let's switch gears. Let's look at that train network problem. We can still use our depth-first search strategy, but the structure of this new puzzle actually lets us use a much more elegant, more specialized version of it. See, a train network is a bit different. It's not just a web of one kind of thing. You've got 2 different types of nodes. You have stations and you have trains. The things connected to a station are trains, and the things connected to a train are stations. Trying to make one search function handle both types just feels kind of clumsy. So instead, we use this beautiful technique called mutual recursion. Rather than one function trying to do everything, you create a team of two expert functions. One is a specialist in exploring stations, and the other is a specialist in exploring trains. And they just pass the job back and forth. And here's our team. You've got Explore Station, whose only job in life is to look at a station and figure out which trains go through it. And you've got its partner, Explore Train, which only cares about which stations a particular train stops at. By giving them these simple, focused jobs, the whole thing becomes way cleaner. The result is like this elegant dance. We start by asking Explore Station to check out Pusawal. It finds a train and tags in Explore Train. Then the train function finds the next station on its route, Igatpuri, and tags Explore Station right back in. It's this beautiful cooperative handoff that explores the whole network. So what have we learned here? What's the big idea? It all comes down to adaptation. We've just tackled two completely different puzzles, but we use the same fundamental strategy to solve them both. The huge takeaway is that depth-first search isn't some rigid, one-size-fits-all tool. It's more like a flexible blueprint for exploration. The really powerful solutions come when you adapt that blueprint to the specific shape of your problem. For the students, that meant building the network as we went. For the trains, it meant using that tag team of functions. And sometimes when you find a solution that's this powerful and this elegant, the reaction isn't some long, complicated explanation. It's just that moment where everything clicks. It's just, oh yeah. Yeah. That's the feeling of discovering a truly fundamental idea. And that's really the thought I want to leave you with. This way of thinking isn't just for computers sorting through data. It's a mental model for exploration, for discovery in any complex system. So the question is, what hidden connections, what unseen patterns are just waiting to be discovered in the networks all around you?